So for this problem, example 3, we want to again determine the concavity and points of inflection for this function f of x equals x squared plus 1 over x squared minus 4. So right off the get-go, we need to figure out the domain. And probably the easiest way to do that is to factor this denominator. So this function becomes x squared plus 1 divided by, and that's, you should notice that's a difference of squares, so that's x minus 2 times x plus 2. And then we can see, okay, the values of x that make the denominator 0 are 2 and negative 2. So the domain would be negative infinity up to negative 2, and then union, and then negative 2 to 2, and then union, and then 2 to infinity. Okay, so that's the domain, all right? So our critical numbers, if we find them, all right, have to come from within the domain, okay? All right, so let's start trying to find the critical numbers for this. So we're gonna have to find the first derivative, and then I would use this and use a quotient rule to find the derivative. I wouldn't use the factored form because that's just gonna be harder to do, okay? So I would use this original form that we have to find the first derivative. So f prime of x would equal, okay, so we gotta take the derivative of the top, which would be 2x, times the bottom, which is x squared minus 4, and then minus the top, which is x squared plus 1, times the denominator of the bottom, which would just be 2x, all over the denominator, which is x squared minus 4 squared. Okay, so right here, our numerator becomes 2x cubed minus 8x. So 2x cubed minus 8x. And then here we're going to distribute, and I'm going to distribute a negative 2x. So that makes negative 2x cubed. And then negative 2x times 1 would be minus 2x. All over x squared minus 4 squared. And then simplifying the numerator, we would wind up with negative 10x over x squared minus 4 squared. All right, so that's the first derivative. So now we need to look at what is the second derivative. So we have to take the derivative of this. So again, we're gonna have to apply the quotient rule. So f double prime of x would equal the derivative of the top, which would be negative 10, times the denominator, which is x squared minus 4 squared, and then minus the top, so negative 10x, times the derivative of the denominator. So we're gonna have to apply the chain rule here along with the power rule. So we're gonna have to bring the power down. So this would be times 2 times x squared minus 4 to the first power, which I don't need to write, and now times the derivative of the inside, which would be 2x. So times 2x all over, and then we got to square this. Okay, so when I square, this is already being squared, so I'm going to square that. That would mean I have a power raising to another power, so I need to multiply the exponents. So this denominator becomes x squared minus 4 raised to the 4th power. Okay, so I'm going to leave this. I'm going to clean this up a little bit. This becomes negative 10 times x squared minus 4 squared. And this is going to become positive 10x times 2 times 2x. So that's going to make 40x squared. So plus 40, I'm just double checking, plus 40x squared. And then times this x squared minus 4. All over, and then x squared minus 4 raised to the 4th. Now looking at these two, okay, so we have a term here, this is a product, and then we're adding this product. We have some things that are in common. So we have a negative 10 that we could factor out. And then we also have and x squared minus 4, because this is x minus 4 to the second power, and this is just x squared minus 4. So the smallest power is the one we can factor out. So this f double prime of x is equal to, so we can factor out a negative 10, like I said, and the x squared minus 4. And I'm going to use a bracket. Okay, so we factor out this negative 10. We also factored out one of these x squared minus 4. So one of these came out. We're left with one inside. So x squared minus 4. And we factor out a negative 10. So what we're left with here is a negative 4 x squared. And this one got factored out. So I'm going to close that up. All over, and then x squared minus 4 to the 4th. Okay, clean this up a little bit. This is negative 10 times x squared minus 4. And cleaning this up, this becomes a negative 3. Okay, so because we have an x squared here, minus 4x squared, this would be negative 3 x squared minus 4. All over x squared minus 4 to the 4th power. Now, something else I can do is I can factor out a negative out of this, and I'd be multiplying this negative 10 by a negative 1. So that makes 10. And this x squared minus, well, and let's go ahead and write. So this, and then this one is going to cancel with one of these. So I have, sorry, hold on, let me go get, hold on, let me grab my whiteout. Okay, so I'm going to start over with this. Okay. All right, so here we go. So this x squared minus 4 cancels with one of these. Okay, so I'm going to be left with, and I'm going to factor a negative out of this. So that makes 10 times, and this becomes 3x squared plus 4 over, and this one cancels with one of these. So I'm left with x squared minus 4 to the 3rd power. Okay, so that's the second derivative. So we're ready to go now. Okay, that's as simple as we can get it. All right. So now to find the critical values, we have to find where the second derivative is 0 and also where it's undefined. Okay. So where is f double prime of x equal to 0? And then where is f double prime of x undefined? So from this function, okay, we can figure out where the second derivative is 0 by setting the numerator, which is 10 times 3x squared plus 4 equal to 0. Dividing by 10, we would get 3x squared plus 4 equals 0. Subtracting 4, we get 3x squared is equal to negative 4. Dividing by 3, we get x squared is equal to negative 4 thirds, and then square rooting both sides, we get x is equal to plus or minus the square root of negative 4 thirds. But we're taking the square root of a negative, which means you're going to get complex numbers, right? But for the calculus that we're doing, all right, we're only concerned with real valued answers. So this isn't going to be a real valued answer. So there's not going to be a real number, x, that causes the second derivative to be 0. So there's no solution to this. Okay, so where it's undefined is when the denominator is equal to 0. So that's x squared minus 4 cubed equals 0. We're going to cube root both sides, and that would give us x squared minus 4 equals 0. This is a difference of squares, so x minus 2 times x plus 2 equals 0, which means x is equal to 2, and x is equal to negative 2. But looking back up here at the domain, our domain had breaks at negative 2 and 2. So these they make the second derivative undefined. However, they're not part of the original domain, okay? So what this tells me is there are no critical numbers. For this function, there's no critical numbers for the second derivative, okay? All right, now, so because there's no critical numbers, we're not going to have inflection points either. Okay, so I'm going to slide this up a little bit. We can still determine the concavity of it, okay, because we still have breaks in the domain. It would be helpful if I knew how to spell intervals, huh? Intervals. Okay, and the breaks happen, so we're going to go negative infinity. We use the domain along with any critical numbers. So there's no critical numbers, so the intervals that I'm going to make my sign chart for are just, it's going to be the same intervals that we have for the domain. So negative infinity to -2, and then -2 to 2, and then 2 to infinity. We're going to do some test points. Let's slide it up some more. And so x is equal to -3 in this interval, x is equal to 0 in that interval, and x is equal to 3 in that interval. And then we're looking at the sign of f double prime rather, okay? And so we're going to look at this second derivative. If I put -3 into this, I'm going to square it, and that's going to give me a positive value, which I'm going to multiply by 3, which is going to give me a positive value. And I'm going to add 4, which would give me a positive value, and multiplying by positive 10, which would give me a positive value. So the numerator here is positive. The denominator, if I put -3, well, I'm going to square -3, which makes 9. I'm taking away 4, but that's still going to be positive. And when I cube it, it's still going to be positive. So when I take x equals -3, that's going to cause any value in here is going to cause the numerator to be positive and the denominator to be positive, which means it's positive on that interval, okay? The second derivative is positive for every x in this interval right here. So how about 0? Okay, so if we put 0 in here and we square it, that's going to give me 0 times 3, which would still be 0, adding 4, which would give me a positive value, times the 10, which would give me a positive value. So the numerator is going to be positive. The denominator, when I square it, okay, so when I square the 0, it's going to give me 0 minus 4. This would give me -4. And then when I cube it, that's going to cause it to be a negative value. So the denominator is going to be negative. And so we're going to wind up taking a positive divided by a negative, which will cause it to be negative. And then when x equals 3, we're going to square 3, and that makes 9 times 3 is positive, plus 4 is positive, times a positive 10, which is going to be positive. So my numerator is positive. And my denominator is 3 squared, which is 9, minus 4, which is going to be 5. That's positive. So the denominator is going to also be positive. So this is going to be positive. And then the behavior of f, this is telling me it's going to be concave up. This is concave down. And this will be concave up. All right. So what are the intervals on which it's concave up? So we would say f of x is concave up on the interval -infinity to -2. And we're not going to include -2 because the function doesn't exist at -2. Okay, so we're not going to include it this time. And then union, and then we're also not going to include 2 because 2 is not part of the domain. So you can't be concave up at an x value that's not part of the domain. So that's why we're not including it, okay? So 2 to infinity, and then f of x is concave down on -2 to 2. All right, and again, we're not including -2 and 2 because they're not part of the domain. And then we could say also, and there's no inflection points. And so you can switch concavity. So like it switches concave from being concave up to concave down. And the reason that's happening is there's a break in the entire graph. So the graph isn't continuous from -infinity to positive infinity. All right, there's actually a vertical asymptote at x equals -2. So to the left of that vertical asymptote, the graph is concave up. In between the vertical asymptotes, -2 and 2, it's concave down. And then to the right of that last vertical asymptote, it's concave up. So that's why you can have changes in concavity without having inflection points, okay? All right, that's it, guys, for example number 3.